Okay, so welcome to this video on temperature and temperature scales. So we're going to talk about the three temperature scales that we will see. We'll actually see two of them in class, but we're going to talk about a third one because that's what we're normally used to using. We're used to using the Fahrenheit temperature scale, and even though scientists almost never use the Fahrenheit temperature scales, well, sometimes we have a conception in our head of how what certain temperatures are, ambient wise. I mean, the atmosphere, how much feels too hot or too cold. What's a hot day, what's a cold day. And we don't normally kind of understand Celsius or even this other Kelvin temperature. We really don't get a sense of how hot or hot cold that is unless we turn it into Fahrenheit. So we're going to use that. So let's take a look at this first slide here. The first slide here says that temperature gives us a definition. Temperature is a measure of the average kinetic energy of the particles in matter. In other words, what you're getting when you're taking a temperature is you're getting a measurement of how fast the particles are moving. So the first little bullet subpoint here says that the more energy, the faster the particles move, and thus the higher the temperature. So when something gets hot, it means its particles are moving faster. If you have stapler made out of metal, and it's at room temperature, then its particles are moving faster. Now, we've talked about how solids have the particles stay in place. They're in a fixed position relative to each other, but they're vibrating back and forth. So even in a solid that's just sitting there, the molecules and atoms that make up that solid have the particles vibrating back and forth. If they didn't have the particles vibrating back and forth, as we're going to find out right now, that means that the temperature is almost 460 degrees below zero. Okay, and so we always have particles moving back and forth unless it's incredibly cold. The particles, when they stop, and there's a point where they do stop, that's a way cold temperature. We're talking 460 degrees below zero, almost, is what will get them to a temperature that will have them stop. So right now at room temperature, the particles are moving. They're vibrating back and forth. Solid, liquid, or gas. In the solid, they're just vibrating back and forth. Liquid, they're moving. They're swimming past each other. And gas, they're bouncing around within their container. As you warm it up, the particles start moving faster and faster and faster. And so as you put energy into it, that's how an object will warm up. The particles start moving faster and faster and faster. And so when we're measuring temperature, we're measuring basically how fast the particles are moving. And there is a distribution of speeds. Some particles are moving faster than others. It's probably easier to think about it in a glass of water. Some of the particles in a glass of water are moving faster, some are moving slower, but there's an average speed. Same thing with the vibrations in our stapler also, is that they're going to have a variety of speeds, but there is an average speed. So what we're measuring is that average speed. And we're going to use, in order to measure these, we're going to use a thermometer. So a thermometer is your instrument that's used for measuring temperature. Now, there's traditional thermometers that basically kind of are a liquid inside of some type of tube, and those liquids, as the temperature gets hotter, those liquids expand a little more, and therefore the liquid's going to go up. And thermometers tended to be filled with things like mercury or alcohol. If you see a thermometer with a red liquid in it, it's probably alcohol, because alcohol expands on heating very well. And if it's a silvery liquid, then it's mercury. Others can be used, but generally those tend to be the ones that we use. Nowadays, though, there's much more technological thermometers. There's basically digital thermometers where there's a sensor that senses the temperature, and so we don't have the little tubes with the liquid in there. So unfortunately, my other program that allows me to use all the functions of Microsoft PowerPoint is not working. So this next slide is supposed to have like things appearing little by little, but I'm not going to be able to go ahead and do that. So let's go ahead and take a look at the three temperature scales. There's Fahrenheit, Celsius, and Kelvin. And let me just go ahead and let you know how they compare and how they came about, so that we have a kind of a better idea of, why they're where they're at. The Fahrenheit scale was the first one. And I think the Fahrenheit scale was invented, obviously, by a guy named Fahrenheit, and probably invented in the mid 1700s. All this guy did was he said, hey, if I get a little glass tube and I put a liquid in it, when it cools down, the liquid contracts and it'll drop down. If I put a bulb at the bottom, and as the temperature drops, it'll contract and the liquid level will move down. As it warms up, then the liquid level will move up as it expands. So there's not more or less liquid in there. It's just it's expanding and contracting with temperature. So that's what he said. And he said, okay, well, let me go ahead and make up a scale. And he went and probably, I think, he plopped it into some snow outside his house, and found that, the snow outside his house was at a certain temperature, put a marking there, and said, that's my 0. Then he went ahead and looks like he plopped it into his wife's mouth or somebody's mouth, and he said, whatever the body temperature is, that's 100 degrees. Person probably had a little bit of a fever, because normal body temperature actually 98.6. 100 is, now you're starting with a fever there, but that's how they made it. And then he made these little markings. He divided the two different markings, the snow outside his house and the person's body temperature, made 100 markings between those, called each one of those a degree. And now he went ahead and had divided into degrees Fahrenheit. He kept with those degrees and he expanded it up and down below, and now he's got his Fahrenheit temperature scale. Now it turns out that one of the important things to know in general is what the melting point or freezing point of water is, because depending on the ambient temperature, the temperature outside, you can expect whether it's going to rain or snow based on whether the temperature is above or below the freezing point of water. So there's this one point called both the melting point and freezing point, because ice melts at the same temperature as water freezes. They're just opposite processes. We call that the melting point, and found that the melting point occurs at 32 degrees Celsius. Okay. Also, turns out that water will boil at 212 degrees Celsius. So if you keep going up and you boil water, once you get to this point, the water doesn't get any hotter, it just turns to steam. Okay, so that's how the Fahrenheit scale came into use. Then someone else came along, scientist named Celsius, and he said, we've had the scale, it works, it's good, but the 0 and the 100 were some crazy numbers. I mean, some random piece of snow outside, and some feverish person's body temperature is not as important as knowing other temperatures. So what he did is he decided to make another temperature scale. Use the same setup for his thermometer, but he decided to change where the 0 and the 100 are. And he decided, you know what? It is more important to know what the freezing point or melting point of water is and what the boiling point of water is. So on his scale, he just marked the 0 at the freezing point of water, which would be 32 degrees on the Fahrenheit scale. He marked it as 0 on his scale. And then the boiling point, he put at 100 degrees Celsius. So that was his 100 instead of 212. Now he went ahead and then took those 2 points, the temperature at freezing point and the temperature at boiling point, and he divided that into 100 pieces. And since there's actually kind of a bigger uh, segment here between the freezing point of water and the boiling point of water versus the 0 and the 100 on the Fahrenheit scale. Turns out that each Celsius degree is a bit bigger than each Fahrenheit degree. Actually, each Celsius degree is 1.8 times as big as a Fahrenheit degree. So 10 degrees 10 degrees Celsius is the same as 18 degrees Fahrenheit. Each Celsius degree is bigger than each Fahrenheit. So therefore, you need more Fahrenheit degrees to make the same temperature change. And that's how he decided that he had his. Okay. So now that we have a new temperature scale called Celsius, the question was how to convert from one to the next. And there's this equation up here. And we have this equation. It's the degrees Fahrenheit minus 32 divided by the degrees Celsius is equal to 9 over 5. Okay. How do we get that? This is what occurred. They made a proportion between the Fahrenheit and Celsius scales. So it said degrees Fahrenheit divided by degrees Celsius, so proportion. The proportion of Fahrenheit degrees over the proportion of Celsius degrees was going to be as follows. Now, before we can go ahead and find a proportion, you got to remember that the 0 for the Celsius is right here. It's actually equal to the 32 for Fahrenheit. So in order for the two scales to start the same way, you have to subtract 32 from the Fahrenheit so that we can have a proper proportion between the two. So that's why there's a minus 32 here, because Fahrenheit, the freezing point of water is at 32. So if we're going to compare the two scales, we have to start them both at 0 at the same place. So they subtract 32 from Fahrenheit. And then let's use a proportion. Now, if you look on my slide here, you can see that from 32 to 212, from the freezing point of water, or melting point of water, whichever one you want to call it, to the boiling point of water, there's 180 degrees. Okay, so there's 180 degrees from melting point to freezing to boiling point in Fahrenheit. In Celsius, for the same change, going from freezing point to boiling point, it's 100 degrees. So there's 180 degrees in Fahrenheit for every 100 degrees there in Celsius. So really, see the side over here, 9 over 5? It used to be 180 over 100. You just go ahead and put the 180 from this guy divided by the 100 from this guy on the Celsius. And then 180 divided by 100, if you divide both the top and the bottom by 20, 180 divided by 20 is 9, and 100 divided by 20 is 5. So all you did is reduce the fraction. And you come up with this equation. And we'll do some sample problems in a little bit as to how you would use this equation. Okay, but all you do is plug in. If you plug in a Celsius temperature here, then you solve for the degrees Fahrenheit. If you plug in a Fahrenheit temperature, you'd solve for the degrees Celsius. Oh, and it's easier if you just flip both sides of the equation if you're looking for degrees Celsius. So you get degrees Celsius over degrees Fahrenheit minus 32 is equal to 5 over 9. So you flip the left side, you also flip the right side. Now you've got your degrees Celsius in the numerator, and that'll allow you to solve it. So that's how we got these first two temperature scales. The third temperature scale came about after the discovery of a thing called absolute zero. It turns out that scientists found back in the 1800s, thanks to some work done by a guy named Jacques Charles, that there is a temperature which you cannot go below. In other words, there is a temperature that you cannot pass and go down and freeze but beyond that. He found it by going ahead, and we're going to be looking at the second semester, but he came up with this thing called Charles' Law. He was looking at the relationship of a gas's volume and its temperature. And what he found was that the volume of a gas got smaller, it compressed as the temperature went down. So if you had a certain amount of gas, and it didn't matter what gas it was, or it didn't matter how much of that gas you had, if you cooled a gas down, let's say you had a balloon. If you cool the gas down at constant pressure, that balloon would get smaller. Or if you put the gas in a piston, that piston will also get smaller, or at least it would suck in. So all these things look like that there was a relationship there between volume and temperature. That was the main thing he was looking for. And once again, once we get to chapter, I think it was 14, we will be using the equations for Charles' law. But another thing he found, kind of what we'll call it corollary, something that came about also, is the fact that all these lines represented how a gas at a certain temperature, how its volume dropped. And all these lines, each one of these were different lines. They had different slopes, but they all converged in the same point. They all converged here at a point 273 degrees below zero on the Celsius scale. And that got people wondering, why do they all converge right there? And that got a lot of study going, and people kind of finally figured out, hey, you know what? That's because at that point, there is zero volume, and there's no more gas at that point. And not only is it at zero volume, it actually, they find out, turns out that all your gas turns into liquid, and liquid turns into solid. And at that point in time, they never got there because you can't get to zero volume, but everything was heading there. They found that there's no way to get below that temperature. That is what is called absolute zero. So on our scale here, you'll see that I have this thing called absolute zero. And on Celsius, well, they found that that temperature, as you saw on the graph, was at negative 273. It's actually technically negative 273.15. They've actually been able to get it down to decimal places. It's been hundreds of years of research that they've had to kind of place exactly where absolute zero is. But if you go ahead and cool things down on the Celsius scale, you can go all the way down to 273 degrees below zero on that Celsius scale. If you were to convert that to Fahrenheit, or if you were to use a thermometer on the Fahrenheit scale, you would find that the Fahrenheit thermometer can also get down to minus 459 degrees. And that was it. And you can't go below that. So those are absolute zeros. And then a guy in England came up and I thought, hey, wait, his name was Lord Kelvin. Why do we have these temperature scales, he said, Lord Kelvin said, why do we have these temperature scales that have negatives on them? I mean, you know, if there is a point where you can't get any colder than, if there is a temperature that is the absolute coldest temperature, then why don't we start our scale there? I mean, you know, Fahrenheit started throwing his thermometer into random snow outside his house. Celsius, you know, at least I kind of understand. He wanted to know whether, you know, a water was going to freeze at a certain temperature or not, so he used the freezing point of water. But, you know, honestly, we can even, what does it mean to have a negative temperature? Plus, when you use negative temperatures in certain formulas, it gives you some weird stuff. There's relationships between pressures and temperatures, and volumes and temperatures, like you saw in Charles. And he said, you know what? If I have a positive temperature and a negative, and I change a gas's temperature from positive to negative, and I have a positive volume that I begin, I'm going to end up with a negative value for volume. What does it mean to have a negative volume? Does that mean I owe space to something else? So there was a lot of problems with having a negative temperature. Usually it's not a problem. Just know that, you know, it's below whatever we decided is zero. But these zeros were relatively arbitrary. So what Kelvin did is he said, well, I like the size on Celsius's degrees. So I'm going to keep that. All I'm going to do is move Celsius scale, instead of starting at zero, instead of the zero being the freezing point of water, I'm just going to move it all the way down to negative 273 on this scale. And so on the Kelvin scale, 0 Kelvin is absolute zero. There is nothing you can get colder than 0 Kelvin. So it's there. All he did though is moved it down. So each scale is a little different. Since he moved it down to 73, now the freezing point of water is 273 Kelvin. And since the boiling point on the Celsius scale was 100, well, then it's just 100 above the freezing point. Since the size of the degrees are the same, then 273 add 100 is 373. That's the boiling point of water on the Kelvin scale. Okay, so that's how we got our 3 temperature scales. And by the way, in order to convert Kelvin to Celsius to Kelvin, it's real easy. All you have to do is take the Celsius temperature, add 273. See, you got 100 right here. You want to turn it to Kelvin, add 273. That's 373. Because all we did was move the scale straight down, right? There was no proportions necessary. If the size of the degrees were different size, then we'd have to kind of get a formula like this with proportions in it. But since this was the same, every degree was the same size. It was just moved down and started elsewhere. Then all you do is add. Right, from 0 degrees Celsius, add 273, becomes 273 Kelvin. Negative 273 Celsius, add 273, becomes 0 Kelvin. That's your absolute zero. Okay, so that's the story of the temperature scales. And let's try some sample problems to convert Fahrenheit to Celsius. Your worksheet's going to have you guys converting Fahrenheit to Celsius and vice versa. And then also Kelvin, but once again, the Kelvin's just adding and subtracting 273. Okay, so let's go ahead and try those. Okay, so let's try a sample problem here. So we have a sample problem right here going on right here. I have the equation up here that I told you about. F the degrees Fahrenheit minus 32 divided by the degrees Celsius is equal to 9 divided by 5. Let's say your temperature was 30 degrees Celsius. You call your friend in somewhere in Europe, France or wherever. They tell you today it's a 30-degree day, and you're trying to figure out, are they using a sweater or what? So this is a question mark. The question is, we have really, it's kind of hard for us to kind of understand degrees Celsius. But degrees Fahrenheit, if we can go ahead and convert it to degrees Fahrenheit, maybe we can get a better sense of how hot or how cold it is. So what we have to do is we have to find degrees Fahrenheit. So what we're going to do is we're going to plug in this 30 degrees Celsius into the equation and then solve for the degrees Fahrenheit. So let's do that. I'm going to go ahead and go degrees Fahrenheit minus 32 all over 30 degrees Celsius is equal to 9 divided by 5. Okay. So all I did was plugged in the 30 here for the degrees Celsius. Now all I have to do is solve for the degrees Fahrenheit right there. It's the only variable left. So in order to get the 30 degrees Celsius away, get the Fahrenheit by itself, I multiply both sides of the equation by 30. Multiply 30 here, multiply 30 here. This way the 30 cancels out. Right, so this 30 cancels out this 30. 30 over 30 is 1. It cancels out. And what I'm left with on the left side is degrees Fahrenheit minus 32. And that's going to equal to 9 times 30. You can use your calculator here. Is 20, I think 270. Let me go ahead and grab my calculator here. 9 times 30 is 270 divided by 5 is going to be 54. So I got on the right side, 9 times 30 is 270. 270 divided by 5 is 54. So I end up with 54. Okay. So now in order to figure out what degrees Fahrenheit is, well, all you have to do is get rid of the negative 32 or the minus 32 on the left-hand side. So all we do is add 32 to both sides, so that now we're left with just degrees Fahrenheit on the left is going to equal to 54 plus 32. That's going to be 86. So it's a nice warm day, right? We know that 86 degrees, Fahrenheit, Celsius. 86 degrees is a nice warm balmy day around here. So that's what 30 degrees Celsius is. You don't have to worry about them needing a jacket that day. You can just go ahead and have them, that you would probably kind of use shorts and maybe no sweater, and you'll be fine. Okay, so that's example number 1. Now let's try a second example. Okay, and so the second example, we're going to go back in the opposite direction. Let's say that you have a temperature. You've taken a temperature of, what shall we say, 100 and, hold on, let me get the right pen. Here we go. good to draw. 156 degrees Fahrenheit. What would that be in Celsius? Now, I hope this is not the temperature for a specific day. That would be way too hot. But, it is kind of a way of, it's just another temperature that we're going to figure out. What is the temperature on the Celsius scale versus the Fahrenheit scale? Now, for this one, I'm going to go ahead and take this tack. I don't like to have to get my unknown, because what we're solving for is a degree Celsius, which is here on the bottom over here. I don't like having to get that out of the denominator. We could cross multiply, and later on we'll see that some of these will cross multiply. But I think the easiest thing to do is, our unknown is degrees Celsius. We have a Fahrenheit temperature we're going to put in here. All right, I'm going to put it right here. So I'm going to go ahead and do that. I think the easiest thing to do is to just flip the equation so that my unknown, the degree Celsius, is on top in the denominator. Makes it easier to solve the problem. So degrees Celsius over F minus 32. Some people say, Mr. Angulo, can you do that? Yes, you can, as long as you do the same thing on the opposite side. So if I flip the left side, I need to flip the right side. All right, because, 1 over 5 equals to 2 over 10 is the same thing as 5 over 1 is equal to 10 over 2. All right, so you can do that. Okay. So all I did was flip it. Now I'm going to go ahead and plug it in over here. I guess I'll do it this side. Just using this sheet here for the first time in a while. So degrees Celsius is what I'm looking for. Fahrenheit is 156 minus 32. That's going to equal to 5 over 9. Okay, so got these guys together. And since I went ahead and already put them together, I plugged in the Fahrenheit temperature, we can go ahead and add them together, and that's what we're going to get is 156 minus 32 is 124. 124. All right. Now, in order to find out what the Celsius temperature is, let me rewrite this here just so it doesn't look confusing. So degrees Celsius over 124 is going to be equal to 5 over 9. Now, in order to solve for degrees Celsius, all I have to do is get degrees Celsius by itself, which means I need to get rid of the 124 from the left-hand side. Since it's in the denominator, all we do is multiply it to the numerator. Multiply to numerator here on this side, so it cancels. And since we multiplied it on the left, we have to multiply on the right. Multiply it by 124. So 5 times 124 divided by 9. Let's see what that ends up being. 5 times 124 divided by 9 is going to give you 68.9. We'll go to decimal place. We'll go over rounding later on in the week, but end up with degrees Celsius is equal to 68.9 degrees Celsius. And there is your temperature for this 156 degrees, 68.9, or 68.9 degrees Celsius is 156 degrees. Okay, so you're going to get a worksheet where you're going to go ahead and be given a Fahrenheit or temperature or Fahrenheit or Celsius temperature. If you're given a Fahrenheit temperature, calculate Celsius like we did here. If you're given a Celsius temperature, calculate Fahrenheit like we did in the previous sample. Okay, so converting from Celsius to Kelvin is pretty easy, but I thought, well, let me go ahead and show an example because I think it helps some people to actually see how it's done. You just add 273 to it, but let's say you're told that your degrees Celsius, the temperature is, let's try 15 degrees Celsius. What is it in Kelvin? Well, all you do is plug it into this equation. Your Kelvin temperature is your Celsius temperature, 15 plus 273. And if I add 15 to 273, I get 288. And just to show you guys, when you use Kelvin units, you don't put a degree. You'll notice that in Fahrenheit and Celsius, we do put these little degree symbols. So 15 degrees Celsius 72 degrees Fahrenheit. But in Kelvin, 288 K or 208 Kelvin, you can say 208 degrees Kelvin, but we don't normally go ahead and put a little symbol like that. Okay, they just keep it at Kelvin. And if I were to give you a Kelvin temperature, like let's say, how hot is 200 Kelvin? How many degrees Celsius is that? Well, all you do once again is plug it into this equation, except you're going to plug it in for the kelvins, right? So you start at 200 Kelvin. 200 is going to equal to degrees Celsius plus 273. And in this case, since the temperature given is on the outside opposite this 273, what you need to do is get the degrees Celsius by itself. So you're going to subtract 273 to both sides. Subtract 273 to both sides. Here, the 273's cancel on the right side, leaving you with direct degrees Celsius. And on the left side, 200 minus 273 is negative 73. And since we're looking for degrees Celsius, we do put degrees Celsius. Okay, so that's how you would use this equation. It's possible that I give you a degree Fahrenheit and ask you for degree Kelvin. There is no equation I'm giving you that's direct, but you can go ahead and go degrees Fahrenheit, convert it to degrees Celsius. Solve for degrees Celsius, like we did in the previous problem. Then once you have degrees Celsius, add 273, and there you get your degrees Kelvin. Okay? All right, so I hope that helps.